Okay, so in this video, we're going to look more into depth on infinite limits. So an infinite limit is a limit which approaches infinity. Okay, so it sounds simplistic. Okay, so it's a limit that approaches infinity. So limit as x approaches some value c of f of x, it approaches either positive or negative infinity. So it either increases without bound or decreases without bound. So let's have a function such like this. Let's have the function f of x equals 1 over x minus 1. So here is our graph. So what is the limit as x approaches c from the left? Well, x approaches 1 from the left of f of x. Well, you could see that as it approaches 1 from the left, it starts to go lower and lower and lower and lower, which means it starts to decrease without bound, which means the limit as x approaches 1 from the left is negative infinity. It will go lower and lower and lower and lower without ever stopping. If you were to check the limit as x approaches from the right, so from the right, you would see that slowly starts to go up and then rapidly starts to go up. So it just keeps going up to infinity. It increases without bound, which means it approaches positive infinity. And we could use the notion of infinite limits to help find vertical asymptotes, which is a word I have used before. And a vertical asymptote is a line. It's like a special line. Okay? So it's a special line. So if x approaches either positive or negative infinity, as x approaches some value, either from the right or the left, that means there is a vertical asymptote there. So you'll have a function such as this. So this is increasing without bound as it approaches a certain value, c. That means there's a vertical asymptote x equals c. So let's see if we can use properties of vertical asymptote. So you can find a vertical asymptote by setting the denominator equal to 0 and basically checking the domain. So let's find all the vertical asymptotes. All the vertical asymptotes at f of x equals x squared plus 1 times x squared over x squared minus 1. So you can't really factor the top one. However, you can factor the bottom. So x plus 1, x minus 1. If we get 0 over 0, that means we can simplify it further. Okay, it's indeterminate, basically. However, if the numerator is not 0, that means we've hit a vertical asymptote. Okay, so, or another way you can find it, if you were to check the limit of the function, either from the left or from the right, if it approaches infinity or some number over 0, okay, that means there's a vertical asymptote there. So at -1, you know it's clearly not defined. We'll make this value equal to 0. However, over here you have -1 squared plus 1 equals 2. So that equals 2 over 0. which is not 0 over 0, so it's undefined. That means there is a vertical asymptote x equals -1. What about x equals 1? Well, the numerator will gain the same result, 2 over 0. So there'll also be an asymptote at x equals 1, a vertical asymptote. Okay? So let's do another one. Let's find the vertical asymptotes of f of x. F of x equals x squared plus 2x minus 8 over x squared minus 4. So you could factor this. In fact, we can factor the top as well. You have x plus 4 times x minus 2 over. Now this is just a difference of squares. X plus 2, x minus 2. Now these two cancel. Okay, that means it's not defined at 2, but that means there's a hole at 2. There's a hole at x equals 2. So it's not a vertical asymptote. You could check it in the original function, and that'll get you 0 over 0, which does not mean there's a vertical asymptote. So what about x equals -2? If x equals -2, that means the numerator will become -2. Actually, the numerator will become 2. The denominator will equal 0, which means the function has a vertical asymptote at x equals 0. X equals -2. X equals -2. Okay. Let's do one more. So these infinite limits are useful to find these vertical asymptotes. Okay, so let's find the vertical asymptotes of f of x equals x over the sine of x. So we have some trigonometric functions going on here. So where are all the values that sine of x equals 0? Well, x could equal 0, x could equal pi, x equals 2 pi, and so on. So it'll just be some integer n times pi. Okay? Now we gotta test these. X equals 0 does not work. Why? Sine of 0 equals 0, but x, the numerator, will equal 0 as well. So f of 0, which is not defined, will be 0 over 0. That means there's a hole. Or not necessarily a hole, but it approaches a value. It's not a vertical asymptote because this will approach a value. Okay? So let's find f of pi. Okay, sine of pi is 0. However, x equals pi, so I have pi over 0. This will also be the same for 2 pi, 3 pi, and some integer n times pi. So we'll have vertical asymptotes at x equals pi, 2 pi, 3 pi, and so on. So our x equals n times pi, where n is an integer. Okay, so yes, so that's really the only major use of the limits that are unbounded to find these vertical asymptotes. So we're going to learn about another type of infinite limit, a limit to infinity, in the next video.